Welcome to Ultimate Sleep Doctor. Tonight, we'll be tracing journeys of immense time. Deep within the heart of ancient glaciers, a silent story unfolds. These rivers of ice, sculpted by millennia, hold secrets of the Earth's past. Scientists use ice cores, cylindrical samples extracted from these frozen landscapes, to unlock a history of our planet's climate. Each layer of ice, formed over countless years, is a tiny window into a changing world. It's a profound thought, isn't it? To know that we are connected to epochs far older than our own. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift like the snow upon a glacier. Let's begin. Let's consider the incredible journey of a glacier, a slow, powerful river of ice sculpted by the laws of physics. It's not a simple, uniform flow. Instead, a glacier moves through a fascinating interplay of forces, all working together to shape its path and form the landscapes we see today. The movement begins at its base, where the ice meets the bedrock. This is where the most complex physics comes into play. The primary driver of glacial flow is basal sliding. This is the process where the immense weight of the ice causes it to creep slowly over the underlying rock. It's not like sliding on a smooth surface. The bedrock is rarely perfectly flat or even smooth. Instead, the ice encounters bumps, cracks, and irregularities. The ice responds to these variations, and this is where friction becomes supremely important. The amount of friction depends on several factors: the roughness of the bedrock, the temperature of the ice, and the presence of water. Now, water plays a particularly crucial role. As glaciers move, they melt and refreeze, creating a persistent zone of meltwater at the base. This isn't just a small trickle, it's a substantial volume of water, sometimes tens of meters deep. This meltwater acts as a lubricant, drastically reducing the friction between the ice and the bedrock. The water effectively flows beneath the ice, allowing it to slide more easily. But it's not just about the water itself. The temperature of the meltwater is also vital. Warmer water is a better lubricant than cold water, again reducing friction. As the ice flows, it tends to warm up, concentrating heat at the base. This creates a positive feedback loop. Warmer water leads to more sliding, which in turn leads to greater warming. Beyond basal sliding, the ice itself is subject to internal deformation. The immense weight of the overlying ice causes it to deform, both vertically and horizontally. This deformation is particularly pronounced in areas of higher slope or strain, where the ice is squeezed and stretched. This internal deformation contributes to the overall flow rate. The steeper the slope, the faster the ice will tend to move. The ice isn't just passively sliding, it's actively reshaping itself. Furthermore, the flow isn't perfectly smooth. As the ice moves, it often develops channels, valleys carved out by the concentrated flow of meltwater and ice. These channels can become incredibly deep and wide, sometimes rivaling the size of the glacier itself. These channels are formed by the erosive power of the flowing ice, which acts like a giant, slow-moving river, carrying away sediment and sculpting the landscape. The wider the channel, the faster the ice can flow, reinforcing the pattern. So, you see basal sliding, internal deformation, and the influence of water pressure are all interwoven, constantly shaping and directing the journey of these magnificent rivers of ice. The enormous weight of a glacier isn't just a simple push downwards. It's a colossal challenge to the very structure of the ice itself. Understanding how ice deforms under stress, how it bends, flows, and changes shape, is a remarkably complex undertaking, revealing a material far more nuanced than just frozen water. The key lies in the way the ice is built, a structure determined by countless tiny crystals working together. Ice isn't a smooth, homogeneous substance. It's a mosaic of interlocking hexagonal crystals, like a tightly packed army of miniature prisms. These crystals, formed from water molecules bonding together, are naturally inclined to align in this hexagonal pattern, and this alignment is the foundation for ice's behavior. The size of these crystals plays a surprising role. Smaller crystals, found closer to the ice's center where pressure is highest, tend to be more pliable. They deform more easily, allowing the ice to flow more readily. Think of a tightly packed box of marbles versus a box of tiny beads. The beads would slide much more easily. Larger crystals, particularly those near the surface where pressure is lower, are significantly stronger and more resistant to deformation. This difference in crystal size creates zones of varying strength within the glacier, influencing the overall flow pattern. Temperature exerts a profound influence on ice's rheological properties, its ability to flow. As the temperature increases, the bonds between the water molecules weaken, making the ice less stiff and more susceptible to deformation. This is why glaciers tend to flow faster during warmer periods. The effects aren't uniform, however. The lower layers of a glacier, where it's coldest, remain incredibly strong, acting as a sort of anchor to prevent the entire mass from simply melting away. The temperature gradient, the way temperature changes with depth, is a critical factor in determining how quickly ice flows. Furthermore, the presence of impurities, tiny bubbles of trapped air or minerals, can dramatically alter ice's flow characteristics. These imperfections disrupt the smooth alignment of the crystals, introducing weaknesses and accelerating deformation. Scientists study the distribution of these impurities within ice cores to understand past flow rates and even reconstruct periods of rapid glacial advance or retreat. The process of ice flow isn't simply a gradual, uniform creep. Instead, it's a complex interplay of these crystal size variations, temperature gradients, and the introduction of stress. It's akin to a network of interconnected pipes, where pressure and temperature create waves that propagate through the ice, influencing the speed and direction of flow. Detailed computer models, incorporating these elements, are continually refined to better simulate the behavior of glaciers, helping us understand their evolution and predict their response to a changing climate. Understanding ice rheology is not just about understanding how glaciers move, but about unlocking a fundamental insight into the behavior of materials under immense pressure and stress, a phenomenon that extends far beyond the icy landscapes of our planet. Glaciers aren't just massive rivers of ice, they're incredibly powerful sculptors, relentlessly reshaping the Earth's surface over thousands of years. Their erosive force stems from a combination of distinct processes, each contributing to the remarkable landscapes we observe today. At the heart of this process is the sheer weight of the ice itself. As a glacier moves, it exerts tremendous pressure on the bedrock beneath it, initiating a series of changes. One of the most noticeable methods of erosion is plucking, also known as quarrying. The leading edge of a glacier isn't just a smooth, flowing front. It's jagged and capable of digging into the rock, especially along joints and fractures. Repeated freezing and thawing cycles, driven by the cold temperatures at the base of the glacier, dramatically expand the ice, forcing it into these cracks and pulling away chunks of rock. Alongside plucking, abrasion plays a crucial role. As the glacier slides over the bedrock, embedded rocks and debris within the ice act like sandpaper, grinding down the surface. The size and hardness of these incorporated particles, ranging from silt and sand to larger stones, determine the degree of abrasion. Denser, harder particles create a more aggressive grinding action, while finer materials produce a smoother, polishing effect. This process is particularly effective in creating smooth, polished bedrock surfaces, often seen on the floors of valleys. Another significant process is stripping, where the glacier effectively removes the overlying layer of soil and sediment. This occurs when the ice mass is thick enough to lift and carry away material, especially in areas with weak, unconsolidated deposits. The glacier essentially acts as a giant conveyor belt, transporting material away from the immediate landscape. This stripping action is vital in creating the wide, gently sloping valley floors that are characteristic of many glacial landscapes. The result of these erosional processes is the formation of distinctive glacial landforms. Perhaps the most iconic is the U-shaped valley. Unlike the V-shaped valleys carved by rivers, glaciers carve out valleys with steep, almost vertical sides and a flat, cross-sectioned floor. This dramatic reshaping is a direct consequence of the powerful, directed erosive force of the glacier. Further defining these glacial landscapes are cirques, bowl-shaped depressions carved high on mountainsides. These are the starting points for glacial valleys, formed by the concentrated erosive power of the ice. And importantly, the material eroded from these areas isn't simply lost. It's deposited as moraines. Moraines are accumulations of rock and sediment from small ridges to vast fields formed at the edges or beneath a glacier. Lateral moraines mark the sides of the glacier, while medial moraines form where two tributary glaciers merge. Ground moraines represent the widespread debris deposited by the glacier as it retreated, and terminal moraines sit at the glacier's furthest extent, marking its final position. These moraines are constant reminders of the glacier's passage and the powerful forces that shaped the world around us. Beneath the vast, frozen expanse of a glacier, a hidden world of water flows. It's not the slow, steady trickle of meltwater seeping from the surface, though that plays a role. Instead, a complex network of channels and rivers exists, entirely subglacial, meaning beneath the ice. These aren't just streams, they're powerful systems sculpted by the very heat of the glacier itself and the relentless pressure of accumulating snow. The initial formation often begins with surface melt, particularly during periods of warmer weather. This meltwater doesn't simply pool, it flows downwards, carving pathways through the ice. These channels, sometimes quite wide and deep, are shaped by a combination of factors: the direction of ice flow, variations in ice thickness, and even the presence of bedrock beneath the glacier. The dynamics of these subglacial rivers are surprisingly vigorous. The ice itself isn't a static block, it's constantly flowing, and the water within the channels acts as a lubricant, accelerating the flow rate and intensifying erosion. Think of it like a very, very slow-moving river racing through a colossal, frozen maze. The water carries sediment, rock fragments, sand, and even clay plucked from the bedrock or dislodged from the glacier's surface. This sediment, constantly mobilized, dramatically alters the channel's shape, widening them and deepening their beds. These channels aren't always straight. They frequently meander, influenced by the unevenness of the underlying terrain. Perhaps the most fascinating aspect is the existence of subglacial rivers that flow through the glacier, carving out tunnels and conduits. These are formed when the pressure from overlying ice causes the ice to fracture, creating pathways for water to surge through. Some of these tunnels can be enormous, spanning kilometers, and they're responsible for transporting vast quantities of water and sediment deep within the glacier's interior. The movement of this water isn't just about erosion. It's fundamentally linked to glacier instability. The presence and volume of these subglacial rivers directly influence the rate at which a glacier flows. Increased water pressure beneath the ice reduces friction, lubricating the base and causing the glacier to accelerate. Conversely, a decrease in subglacial water flow can lead to a slowdown, as the ice becomes more rigid and resistant to movement. Scientists study the patterns of sediment deposition, the locations where these subglacial rivers have slowed and deposited their load, to understand the glacier's dynamics and anticipate potential changes in flow rate. Furthermore, the water doesn't just sit within the glacier. It can interact with the bedrock, accelerating erosion, and even triggering glacial, like outburst floods, events that have significant consequences for downstream communities. Monitoring these systems provides a critical window into the future behavior of glaciers around the world. The process of obtaining an ice core is a truly remarkable feat of engineering and scientific dedication, allowing us to peek directly into the history of our planet's climate. It's not simply digging a hole in the ice. It's a carefully orchestrated operation designed to preserve the ice in its purest form, safeguarding the tiny clues hidden within. The journey begins with the selection of a suitable ice mass, typically found in areas of stable, thick ice sheets, like those of Greenland or Antarctica. These locations minimize disturbance and ensure the core's integrity. Drilling itself utilizes specialized hot wire drills. These aren't like the drills you might find at a construction site. Instead, they employ a heated wire, often made of steel or titanium, that melts a precise, circular hole through the ice. As the wire melts, a coolant, typically a mixture of water and glycol, circulates around it, rapidly removing the molten ice and preventing the wire from overheating and failing. The drilled ice is then extracted using a rotating drum, effectively pulling the core upwards. Sophisticated monitoring systems track the depth, temperature, and pressure at every stage to ensure consistent drilling. Once extracted, the core is carefully transported to a dedicated analytical laboratory. Here, the core is meticulously examined and prepared for analysis. One of the first steps is often the removal of larger, irregularly shaped pieces of ice that could compromise the core's structure. This is typically done using a process called sawing or coring saws, designed to minimize ice fracturing. The core is then carefully split lengthwise into two halves for detailed examination. Within these halves, scientists utilize a range of instruments to extract valuable data. Optical instruments, such as spectrophotometers, analyze the ice's light-absorbing properties, providing information about the concentration of gases like carbon dioxide and methane trapped within. Mass spectrometers precisely measure the isotopic ratios of these gases, offering a powerful tool for reconstructing past atmospheric compositions. Temperature measurements are taken throughout the core using sensors that directly contact the ice, providing a record of past temperatures. Beyond gas analysis, ice cores also contain layers of dust, volcanic ash, and even ancient microorganisms. Scientists carefully analyze these materials, identifying volcanic eruptions based on the presence of ash and using isotopic signatures to determine their age. The presence of trapped air bubbles provides a direct snapshot of the atmosphere's composition at the time the bubble formed. Quality control is paramount. Every step is documented, every measurement verified, and samples are meticulously handled to avoid contamination. Regular checks on the core's stability, temperature, and air circulation are conducted to ensure the preservation of this frozen time capsule. It's a delicate dance between human intervention and the natural processes that shaped the ice itself. The data gleaned from these cores are then combined and analyzed, painting a picture of past climate fluctuations, a story written in layers of ice, waiting to be unlocked. The secrets held within ancient glaciers aren't just about the ice itself. They're a remarkable archive, a layered record of Earth's past. Scientists carefully extract data from these frozen time capsules, and much of this information comes from analyzing the subtle variations trapped within the ice. One of the most powerful tools they use are oxygen isotopes, specifically delta O and delta D. These isotopes are different forms of oxygen, and their ratios within the ice tell a story about the temperature of the water that originally formed the snow. When water evaporates, the lighter isotopes, like delta D, tend to disappear more quickly, leaving behind a higher proportion of the heavier oxygen isotope, delta O. By measuring these ratios, researchers can estimate how warm or cold the climate was when the snow fell, sometimes going back hundreds of thousands of years. Beyond oxygen, ice cores also contain tiny bubbles of ancient air. These bubbles, formed when carbon dioxide, CO2, and methane, CH4, were trapped in the ice, provide a direct measurement of greenhouse gas concentrations from the distant past. The concentration of these gases is a crucial indicator of climate change. For instance, a sharp increase in CO2 levels within an ice core corresponds directly to a period of warming. Scientists use sophisticated instruments to accurately measure these gas levels, allowing them to reconstruct past atmospheric composition with remarkable precision. But the story doesn't end there. Ice cores aren't just about gases and isotopes. They also hold clues about the atmospheric dust and aerosols that were present at the time the snow fell. By analyzing the size and concentration of these particles, things like volcanic ash or sea salt, researchers can understand the conditions that influenced weather patterns and potentially triggered climate shifts. Volcanic eruptions, for example, can inject large amounts of sulfur dioxide into the atmosphere, which reflects sunlight back into space, leading to temporary cooling. The presence of specific types of aerosols within an ice core can therefore provide evidence of these events. Furthermore, scientists can examine the ice itself for trace amounts of other elements, such as mercury or lead, which can offer insights into human activities and industrial pollution during past periods. The layering within the ice core is incredibly precise, measured in annual increments, and each layer acts like a tiny, frozen diary. Each bubble of air, each isotope ratio, and each particle of dust contributes a piece to a complex and increasingly detailed picture of Earth's climate history. The data gleaned from these ice cores are not just numbers. They are a testament to the interconnectedness of our planet's systems and a powerful tool for understanding the challenges we face today. The heart of reconstructing Earth's past climate lies within the frozen secrets held by ice cores. But simply having a long cylinder of ice isn't enough. It's the careful, sophisticated analysis that transforms it into a powerful historical record. Scientists employ a range of statistical techniques to tease out meaningful patterns from the data, beginning with what's called trend analysis. This involves looking for consistent changes in various measurements taken at different depths within the ice core. For instance, they might examine the concentration of greenhouse gases, like carbon dioxide, and observe if these levels consistently rose or fell over time, a clear indicator of warming or cooling periods. The data isn't always straightforward. The ice itself has absorbed gases over centuries, so the concentrations within the ice don't perfectly reflect atmospheric levels at the time the snow originally fell. Calibration is a crucial step to address this. Scientists use mathematical models and, importantly, analysis of air bubbles trapped within the ice to correct for this memory effect. These bubbles, preserved for millennia, contain air samples directly from the atmosphere at the time the snow was forming. By comparing the gas concentrations in the bubbles with the concentrations measured in the ice, they can establish a reliable relationship. However, even with meticulous calibration, uncertainties remain. The accuracy of a paleoclimate record depends heavily on the spacing of the measurements. The finer the resolution, the more frequently data is collected, the more detailed and reliable the reconstruction. Scientists often create error bars around their estimates, reflecting the range of possible values based on the available data and the inherent uncertainties in the measurements. These error bars aren't just about saying, "We don't know exactly." They represent the genuine degree of variability in the past climate. Statistical methods extend beyond simple trend analysis. Sophisticated modeling techniques, often employing time series analysis, are used to identify cyclical patterns, such as the Milankovitch cycles, variations in Earth's orbit that influence the amount of solar radiation reaching different parts of the planet. Examining the correlation between these orbital cycles and the climate record within the ice core allows scientists to understand how external factors have shaped past climate changes. Furthermore, the isotopic composition of the ice, specifically the ratios of oxygen isotopes like delta O and delta D, provides a powerful independent check on the greenhouse gas data. These isotopic ratios are sensitive to temperature, offering another way to assess past climate conditions. Combining data from multiple proxies, greenhouse gases, isotopes, and aerosols creates a more robust and confident picture of the past. Ultimately, reconstructing past climate is an iterative process, a continuous refinement of our understanding based on ever-increasing datasets and improved analytical techniques. Each new ice core adds another piece to the puzzle, strengthening the historical record and allowing us to better understand the complex forces that govern our planet's climate. The immense ice sheets of Greenland and Antarctica and the glaciers dotted across the world are facing a truly unprecedented challenge. For millennia, these frozen giants have moved slowly, carving valleys and shaping landscapes, responding to subtle shifts in the sun's energy and atmospheric patterns. However, the rate at which they are now changing is astonishing, and it's all connected to the warmth creeping into our planet's system. Scientists are using ice core data, combined with sophisticated climate models, to understand exactly how vulnerable these icy landscapes are and what the future might hold. Ice cores, essentially time capsules of the atmosphere, provide a crucial record. The deeper we drill, the further back in time we reach. The trapped air bubbles within the ice contain snapshots of the atmosphere from hundreds, even thousands of years ago. But more importantly, the ice itself holds information about the temperature and composition of the air at the time it formed. Analyzing the isotopic ratios of oxygen and hydrogen within the ice, delta O and delta D, is a key way to estimate past temperatures. Heavier isotopes like 18O are preferentially incorporated into the ice when it's colder. Currently, the Greenland ice sheet is losing mass at an alarming pace. Satellite observations and ground-based measurements show that surface melt is now happening earlier in the summer and lasting longer, fueled by rising air temperatures. This meltwater then flows over the ice surface, creating a lubricating layer that accelerates the flow of the glacier. Similarly, the West Antarctic ice sheet is particularly vulnerable due to warmer ocean water circulating beneath it, accelerating basal melting that occurs at the bottom of the glacier where it meets the sea. Climate models, built upon the data gleaned from ice cores and other observational records, are predicting significant further ice loss. These models aren't perfect, of course, and contain inherent uncertainties, but they consistently show a strong link between increased global temperatures and accelerated ice sheet melting. Some projections indicate that if we continue on our current trajectory, we could lose between 1/2 and 2/3 of the Greenland ice sheet and a substantial portion of the West Antarctic ice sheet by the end of this century. The implications are enormous. A significant loss of ice from Greenland and Antarctica would contribute dramatically to rising sea levels, threatening coastal communities and ecosystems worldwide. It also impacts global ocean currents, which are influenced by the influx of cold, fresh water from melting ice. The data from ice cores isn't just about the past. It's a warning, a guide, helping us understand the consequences of our actions today and informing the urgency needed to address the climate crisis. Scientists continue to refine these models, incorporating new ice core data and advancing our understanding of these complex, frozen systems. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds one peaceful night at a time. The ancient flow of glaciers, captured within the ice cores, whispers secrets of time and the Earth's patient journey. Let your thoughts drift, calm and unhurried, like snowflakes settling softly. Allow your mind to find its quiet place, a sanctuary of stillness. Good night.